Now, of course, in applications, you do not have only circuits where you have only a single electromotive force or a battery and a single resistance connected. You have many resistances. You might have many devices connected to the same power supply. Like, for example, you might have many light bulbs connecting to the same battery. And so, in this case, we will not have the simple, nice circuit where we have only a battery and a single load resistance. As an example, consider the simplest example where I have more than one load resistance. I have two load resistance in this case, for example, a battery, and I have two light bulbs connected to this battery. Okay, so this is the battery, this is the power supply, this is the first light bulb. It has its own and its load resistance 1, R1. The other one has load resistance 2, it's R2. So this is real life situation. If you draw a circuit diagram representing this situation, this is how it looks. So we have, this is the electromotive force. Now here we are ignoring, it's irrelevant. This is why we're ignoring the internal resistance of the electromotive force. And these two batteries are drawn in this way. Note we draw them this way because in the real device, the same current is flowing through both of them. So this is why this current doesn't split. Actually, the same I is flowing. So I1 and I2 are equal to I, okay, where I is the current through the battery. So this is the situation. Now we want to find a basic equation for such a circuit. I mean, how we can find the current. Now the idea is the following. If we look at these together, assume that there is a box enclosing these two. And what you see is you see I coming in and I coming out, and you see just there's 2 points, A and C, which are at the same potential delta V as the terminals of the electromotive force. Why? Because A is the same as the same potential at this positive terminal, because there is no circuit element between A and this positive terminal, and also C is at the same potential as this negative terminal. Negative means the one terminal at the lower potential, because there is no circuit element between C and this point. Okay, so in this case, if they are enclosed in the box, it looks like something like this. Okay, you have just a single electromotive force, and as if a box containing a single resistance. Now, how is this, if this is a single resistance of this box, how is this, the resistance of this box related to these two? We say this in the following terms. We say that we replace these two resistors by a single equivalent resistance, and when they are connected in this manner, what do I mean by this manner? When the same current is passing through them, we say that they are connected in series. Okay, connection in series, two resistances are said to be connected in series if the same current is piercing them. Each of them. Okay, so I1 is equal to I2 in this case. So in this case, they are connected in series. Now, the equivalent resistance of these two resistances in this case turns out to be equal, when they are connected in series, turns out to be equal to their sum. Simple addition. Now, how is this? I'm going to derive what is this. I'm sure that this relation is familiar to almost all of you. I've seen this before. So to derive this relation, we first start with the observation that I1 equals I2 equals I. I mean, the same current is passing through the whole circuit, and it's the same current that passes through R1 and the current that passes through R2. Now, delta V, the potential difference delta V, which is between point A and C, which is VC minus VA in this case, is equal delta V1, the potential difference across the first resistance, plus the potential difference across the second resistance. And because it is VC minus VA, okay, so it is positive. So delta V1 plus delta V2. Delta V1 is I1 R1, delta V2 is I2 R2, so delta V is equal to this. Now, if you look at this circuit, the potential, this potential is equal I multiplied by the equivalent resistance of the whole circuits, okay? And since the I1 and I2 are equal to I, then actually, and since this is delta V, then on the right-hand side is this. Instead of delta V, I can write down also I R equivalent, cancel I out, and you get R equivalent equals R1 plus R2, the simple result. So that's what you get. Now, if we have more than two resistances connected in series, the same current passing through the M, if you have n of them, then the result will be the following. Their equivalent resistance will be just the sum of all of these resistances. Okay? Remember, you have to understand that in this case, series connection means the same current is piercing all these resistances. The current is not split. But what splits is the potential. So the potential between this point A and B now is divided across R1 and across R2. Therefore, series combinations of resistances are sometimes called potential dividers. Potential dividers. Okay? This is a good checkpoint to check your understanding. So please try to do it before you proceed. Now, resistors in parallel. There is another combination of resistances in a circuit, so which is here, as you can see. So this is the device. I have two light bulbs also connected to the battery, and they are connected in a different manner here. The thing that you can probably see is that the current that is coming out here is split into two. One goes through this, and one goes through this. So we have I1 going through this bulb, and I2 is going through this. The current splits here into I2 and I1. I1 passes through this, and then they're combined. When they come back, they are just I. So I is coming here, it's splitting into I2, I1, and then it connects again. So diagrammatically, we represent this in the following circuit diagram. Okay? So these are R1 and R2. Now the observation that we make here is the following. We say R1 and R2 are connected in parallel in this case. And why is this, or how we define connection in parallel? The potential difference across R1 and R2 is the same. This is the only criteria to tell that two resistors are connected in a way that we call parallel connection, or that to say that two resistors are connected on parallel. And to understand this, look, this point and this point are at the same potential. This point and this point are the same potential. So the potential across this and the potential across this are the same. And in this particular example, it is also equal to the potential across the power supply. The potential across the power supply. So it's also the same. Okay? So in our example, this is what's happening. Now, again, we assume that if we put a box to enclose, imagine a box enclosing these two resistances, then actually what we will see is a single box. There is a current coming. This is a current going out, and this is the same current, I. Okay? Although inside the box it's split into I1, I2, but when you put it in a box, it's not splitting. You see I coming and I going. Okay? And so we can think of this box as being a single resistance, regardless of what happened in. Now, of course, we formulate this formally by saying this amounts to replacing these two resistances by a single resistance which is equivalent to them. So this is how it looks. Now, the resistance of this equivalent resistance of these two is given by this equation. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Okay? Now, the current that passes through this equivalent resistance is I. The current passing through, in this particular example, is the current passing through the battery. However, each of these R1 and R2 have their own currents. Well, evidently, needless to say, that I is equal to I1 plus I2. And when you add up these I1 and I2, they should add up to I. Because of conservation of charge. Electric charge doesn't disappear. So if it splits, then it goes nowhere. I mean, when you recombine, they will just give the same current. Okay? So that's what I say. So let's derive this expression. Well, the first thing is I equals I1 plus I2. And I1, the current through this, is equal delta V, because delta V is the same here, across this, across. Delta V over R1, plus the second current is delta V over R2. So substituting for I1 and I2 in terms of these, you get this expression. Now, delta V is the same all over, and so here also, the potential difference across the equivalent resistance is just delta V, and the current through the equivalent resistance is I, so we write I is equal delta V over R equivalent. So take this and put it to here. So say that the I, this one, you replace it by delta V over R equivalent, and I1 and I2 replace them by these two expressions. Okay. Now, since delta V is the same, so delta V1, delta V2 is equal to delta V. They are all the same, so you can cancel out these and you get this expression. You get this expression. And if you have more than two resistances, n resistances connected in parallel, the parallel meaning, the meaning of parallel in this context is not that they are drawn parallel to each other. No, then it means that the potential difference across these resistances is the same. So once that's maintained, then you can replace all of these by a single equivalent resistance whose magnitude is related to the magnitude of the other resistances by this simple relation. This is another checkpoint similar to checkpoint 2, which also worth considering before you proceed.